Okay, in today's class, we are going to continue our discussion on what we started with. This is the nitty-gritty of low-level control in a sense that we have a quadcopter and now we want to design a controller for the quadcopter. As discussed in the last class, the most important part of this lesson is implementation of the algorithms on a hardware. So as I discuss some of these slides, I give you sort of an architecture of how it works. Then I'm going to take you to the hardware. So we are going to program the Mambo, and hopefully we would continue to add the inner loops and outer loops so that the Mambo would be able to hover. So we talked about model simplification. So remember the equation for hover that we are implementing, they come from the model simplification. We are going to implement position control, attitude, which is the roll and pitch control. Then we will talk about the control allocation, and we are going to talk about the motor control. So first and foremost, I just want to make sure that you are able to implement complementary filter. Everyone got complementary filter working? Is it working the way you expected or no?
Yes.
Okay. Now what we want to do is we want to use that complementary filter to implement the stabilization control. And once I discussed what the steps are, we will go to the Mambo, and then I will show you how it can be done using the motor mixer that is implemented in Mambo. Did anyone try to control the motors in Mambo? Any luck controlling the motors? You always get variable error. You never get fixed error. Okay, so this is the basic logic. So you have an inner loop and then you have an outer loop. The innermost loop is always related to attitude control. So unless your roll, pitch and yaw are stabilized, your Mambo is not going to fly in a steady flight. We are going to talk about how it is implemented in actual framework. Now, please understand the innermost control that we are looking at. The innermost control that we are looking at is the altitude control. And what is the input to the altitude control? Attitude control. The attitude control is the output of the complementary filter, which is the pitch and the roll is fed onto the attitude control. And this attitude control is basically controlled using a simple PID that is running in the innermost loop. So this PID is running in the innermost loop, and this PID would actually signal out to the motor controller, which is in our case the motor mixing algorithm, and then that would actually stabilize the multicopter. And please understand, multicopter is an under actuated system. There are 6 states, but only we have control over 4 rotor speeds. So we are going to use that to control the overall behavior of the Mambo. Now, this is what we talked about in last class, but very quickly, I just want to add what's happening here. So if you recollect, in the last class, we talked about these 2 equations. The last class, we talked about these 2 equations. And what these 2 equations are? These 2 equations are, this simply means that omega x, omega y, and omega z, which are the body rates. The omega x is about x-axis, which is nothing but the roll rate. Omega y is about the pitch axis, so this is going to be the pitch rate, and omega z is going to be the psi rate. So basically, the body rate are equal to attitude rates when two coordinate systems, the north is down and the body coordinate system is aligned. That's what this means. The second equation is J is equal to omega J B body rates tau. What that means, this equation is nothing but T is equal to I times alpha, where T is equal to torque, and then this I, and this equation I'm going to write this explicitly. So J is going to be Ixx, Iyy, Izz. There will be 0, 0 over here. Then you are going to have omega x dot, omega y dot, omega z dot is equal to tau x, tau y, tau z. So this model, these two equations will be implemented in our autopilot or in the stabilization algorithm. So these two equations, they simplify the model, and gradually, depending upon what we want to do, is we can make these equations more and more complex. Now, next part, which we did not talk about, but at this point, I just want to introduce. We'll talk about these equations a little bit later. Assuming we get attitudes to stabilize, which means our Mambo or our quadcopter is stable in hover, roll, pitch, and yaw. Everything is stable. Now, what we want to do is we want to control its position, which means either we want Mambo to be at x is equal to 0, y is equal to 0, and non-zero z, z is equal to 0, which means it's on the ground. So non-zero z. But we want it to go from say maybe x is equal to 10, y is equal to 10, and z is equal to say 20 meters, something like that. So the equations that we need to implement, they are given as px double dot, py double dot, and pz double dot. So those are the position equations that we are going to implement. Now, please try to understand there is something important that happens. What we have is we have an under-actuated system. What we have is we have an under-actuated system, which means the Mambo in the stable hover cannot go left, right. So what it needs to do is it needs to roll or pitch and then travel in that direction. So here is what's going to happen. So if you look at the accelerations in the x direction and acceleration in the y direction, both of these will have some type of coupling between the roll and the yaw. And I want you to understand this very important concept. So can you see that here this psi is indicative of yaw, phi is indicative of roll. So what you have is when the aircraft is going to, or a quadcopter is going to go forward, or when the quadcopter is going to go sideways, there will be some type of coupling between the roll and the yaw. And clearly the quadcopter cannot travel at 0 roll and 0 yaw. It needs to tilt and then it can go forward. So something like that you will have to take into account when you design the control algorithm. But now I want you to understand two things that are going to take place, and that is where the state flow comes in the picture. When your quadcopter is in stable hover, requirement is the roll is to be 0, pitch is to be 0, and yaw is to be 0. But when the quadcopter is going to go forward or sideways, it cannot do that when the roll or when roll is 0. So what you need to do is you need to relax the stabilization algorithm and provide some non-zero value for the coupling terms so that that quadcopter can go forward or backward. I don't know if you understand this concept, but this is what it means. If the quadcopter is in stable hover, your roll angle is basically 0. So when your roll angle is 0 and when your pitch angle is 0, can you see that what that means is your, I don't know if you see, let me write this down. So imagine your roll angle is 0. So this term becomes 0. Your pitch angle is 0. This term becomes 0, which means the horizontal acceleration becomes 0. So which means the quadcopter cannot move horizontally. So what you need to do is you need to relax one of those assumptions. So what you should do is when you provide a forward translation command, you would say now your stable operation point is not at 0 degree maybe pitch, it's at maybe plus minus 2 degree pitch. That way the quadcopter can pitch down or pitch up and basically travel in the forward direction. Same thing happens when you want the quadcopter to go left. So again, please understand, if your sine value, basically sine phi and sine theta, if they are 0, there is no way the quadcopter can travel in the horizontal direction. So what you want to do is you want to relax one of those assumptions, only then your quadcopter can travel in the y direction. Everyone understood this? So what does this mean when we implement the low level flight control? So here is what it means when we implement the low level flight control. And please pay attention because we are going to implement this. In the last class, we talked about the hover. The quad is flying in a stable hover. Everyone understood the algorithm that we talked about in last class? How would we achieve stable hover? We find the roll and pitch, use the complementary filter. The value coming from complementary filter is the error, and we would actually give a command signal proportional to the error. That would be our proportional controller. If we implement the error dot multiplied by some constant and feed that to our motor mixing algorithm, that would be proportional and derivative control. Usually integrating control will not be needed in this particular case. Now let me ask you this question, that assuming our hover works, and now I want to implement the forward motion. I want to implement forward motion. If I want that quadcopter to go in forward motion, do you agree with me that my py double dot or basically the acceleration in y direction has to be 0, but my acceleration in the x direction has to be non-zero? You agree with me? So how do I implement non-zero acceleration in the x direction? Step 1. So if I want to implement the forward motion, I'm going to deliberately allow pitch to vary. So I'm going to say my theta, which was initially the set point was initially 0. Now my set point would be say 2 degrees. And as soon as my set point is 2 degrees, please note that this entire equation is going to get changed. So my roll is 0, but this entire equation will get changed by cosine phi sine theta. So P x double dot is equal to cosine phi sine theta. And then I would have this f by m, f by m. And this sign, yeah, this positive, there is a negative sign here. And what I would do now, I'm going to change this f by changing the speed. Are you with me so far? Now, the story doesn't end there, because what's going to happen is, as soon as I make my theta is equal to 2 degrees, recognize what happens here. I'm going to say my role is basically 0, but still I get an undesired effect from this term which is appearing in the equation. Are you with me so far? So which means because I pitched, what happened, and I want to go forward, but because of the coupling that I have over there, actually I get that term. How would I eliminate that term? The only way I can eliminate that term is to ensure my heading is 0. Are you with me so far? So what I would do is, I would allow theta is equal to 0, but my psi is equal to 0, and my role is equal to 0. Only then my quadcopter can go in forward direction. Everyone understood this? Everyone understood this? Yes. Similarly, if I want to go in the lateral direction, same logic. My phi, I would restrict to maybe a very small value. I tell you the reason why it is small. Because the control that what we are using is a PID control. PID control works very well when the variation from the equilibrium is small. So which means if your quadcopter is at 45 degrees, PID will not get it back to 0, because that is not the domain of operation for the PID. If your quadcopter gets disturbed by 10 degrees, 15 degrees, PID may work. If you want the system to be stabilized at high angles, then you will have to do something called as maybe model predictive control, or some type of advanced control algorithm, or maybe gain scheduling algorithm, some type of control algorithm that is better than a simple PID. So I hope that you will build that Mambo pendulum, and then I want you to observe that, assuming you are able to get those coefficients correctly, your Mambo would be stabilized for maybe 10 to 15 degrees. But as soon as you rotate that beyond 25-30 degrees, you will notice, rather than PID stabilizing the system, it would destabilize the system. So next thing is same argument, psi is equal to 0, and you are going to have some py equation minus f by m, and then you can actually have the lateral motion. Everyone understood this? This is the crux of simple hover and forward and leftward. Now, if you look at those toy UAVs that they are in the market, they can do flips. For example, Telo can do 8D flips and all that type of stuff. The algorithm that you need to perform those super complex maneuver are very, very complex. So that's why, even though you see that they are performing these maneuvers, or a $10 drone is performing the flips, slips, 8D flip, 4D flip, but to stabilize a drone to that complex maneuver needs more sophisticated algorithms. And I don't think I will have time for that, but what I would do is, I would just give you how would it work for path. So for an example, if you have a drone that is going from point A to point B, and there are different algorithms for path planning. So what you do is, the easiest way what you do is, you actually do something called as look ahead. So what it means is, basically, you know, you want to go from point A to point B. So you actually have these points. Yeah, question. So what you do is, you basically divide that into these waypoints which are extremely close to each other. And the local control, what it's going to do is, it's going to go from point A to point, say, C, then from C to D, D to E, E to F, and that way that whole path would be covered. We'll try to see how it can be done. And then once you have obstacles in between, then the things become even more complex. But everyone understood how are we going to implement the algorithm for forward motion? Now, the last part which I want to talk about is implementing the algorithm for the up and down. So this is forward, this is left or right. Now, last thing is up and down. Up and down is actually very simple. For up and down, you're going to specify theta is equal to 0, psi is equal to 0, phi is equal to 0. And what you would do is, you would increase the motor thrust. You would increase the motor thrust. So that way, now when your theta is equal to 0, when your phi is equal to 0, can you see that this guy becomes 1? This becomes only 1. And what this means is, your upward or downward acceleration is just function of the thrust that is generated by motors. So increase the speed, it will go up. Decrease the speed, it will go down. Everyone understood this? So the way we are going to implement our algorithms onto Mambo is, first we are going to establish a stable hover. It's not going to be easy. You will have to go through a lot of iterations and verify. Then second step would be, we would do up and down. So basically, you specify a particular value of height, and our Mambo that is in stable hover should be able to go to that particular height. And afterwards, we'll try to implement positive X, positive Y, negative X, negative Y. Everyone understood this? My online students, any questions, concerns?
No questions.
Yeah. No questions? Good. One question?
On the Z direction acceleration formula, the G minus F by M, right?
Yeah.
If I increase the thrust, obviously it is going to increase the force.
Yes.
Then G minus F by M will give me less value.
Correct. But it's going to be in the positive direction. So that G is always going to be present.
It will be in the like downward.
So it again depends upon what axis you choose. So essentially, what I'm trying to say here is, your thrust is always going to be upward. You will never have thrust going downwards. In this particular case, basically the equation is written as G positive because the coordinate system is different. But in our northeast down coordinate system, our G is going down and our F is going up. So this equation is written because the coordinate system is different. But other than that, implementation is the way I discussed. So now I'm gonna go to Matlab, and the first part of Matlab is, I'm gonna show you how to control the motors. Did anyone figure out how to control the motors? So first, I want to open Matlab. And this would be a good time for you guys to open Matlab. Then open Simulink. In Simulink, go to Simulink support package for Parrot mini drone. Now, to be honest with you, you can use any of these templates. You can use flight simulation template, or you can use code generation template. So let me just use code generation template. So it will create this model. Now in this code generation template, if you double click the flight control system, this is the overall structure of the control system. In the last class, we spent significant amount of time on implementing complementary filters on sensors. Do you agree with me? In today's class, I'm going to look at the motor mixing algorithm, which is on the right hand side. So what you have here is this is the motor mixing algorithm. This is the PWM that is fed to motor 1. This is the PWM that is fed to motor 2. This is the PWM that is fed to motor 3. And this is the PWM that is fed to motor 4. Now, what I'm going to do is, first, I'm going to show you, first thing first. Out of these motors, which one is motor 1, which one is motor 2, which one is motor 3, and which one is motor 4? Really? How do you know that? So what I'm going to do is, I'm just going to first run this blank code. Don't turn on your Mambos. First, let me turn on my Mambo, pair my Mambo, and then so let me see if I can turn on my video. Can you see the Mambo? So Mambo turned on. You have to go to Bluetooth, personal area network. Connect using access points. And it should connect. Then what I'm going to do is, just to see how it functions, I'm going to make a small change to this code. So I'm going to go to simulation, library browser. Then I'm going to go to commonly used blocks. Then I'm going to go to scope, grab this scope and place over here. So grab this scope and place over here. And then I'm going to grab this scope from here and attach it. You can actually attach it to either individual PWMs or finally, or the PWM vector that is fed to the saturation block. So I'll tell you what is happening. So when you are dealing with the practical robots have their own limitations. You cannot provide them the input that is beyond the capabilities of the hardware. So what this saturation block does, it's sort of a fail safe. For example, somehow your controller algorithm becomes unstable and it generates the PWM that is beyond the capability of the hardware. In that case, you have the saturation block that limits that PWM. So you would see saturation block almost everywhere when you deal with practical systems. But what I want to do here is I want you to quickly attach this scope here. After scope is done, I want you to go to hardware, and now I want you to click not build deploy, but monitor and tune, and the Mambo's eyes will glow red. Check this out. Monitor and tune. So once you do monitor and tune, Matlab will do its thing. And then it will build, it will flash. It will not take time in extend mode. So online students are missing all the fun. Question? Question? Okay. Start. And then I want you to open this block. This code. So now I want you to notice what? So basically, it is sending 4 PWMs, but those PWMs are not sent simultaneously. Those PWMs are phased, so that what you have is, check this out. This is the first motor, second motor, third motor, fourth motor. Are you with me so far? Oh, online students may not know. Can you see Mambo's rotors playing? So this is first, second, third, the first, second, third, fourth. First, second, third, fourth. First, second, third, fourth. So I'm plotting all 4 PWMs at the same time. I would encourage you to plot those different PWMs differently. Now, what is happening here? If you look at each PWM, so I'm going to stop. Stop. And now what I want you to do is, you can delete this and just connect this to the first PWM. And the reason I want to do this is, before you generate your own control signal, you can't generate a random PWM. It will not work. So whatever PWM that your control algorithm is going to generate has to have certain structure. Now we need to know what is that structure. So let's understand how is that PWM, which means what is the magnitude of the PWM, what is the width of the PWM, at what frequency that PWM is generated, and what is the switching frequency. So I want you to connect here and repeat the same exercise. What? Question? And now you would just see the PWM that is fed to the very first motor. Online students, any question? Once you start, once you open, now you will see the actual PWM that is fed to the very first motor. So what you have is this is the PWM that is fed the first motor. Are you with me so far? Online students, any questions? I'm going to stop and I want to look at this PWM very carefully. So I want to know the characteristics of this PWM. So I'm going to click on this PWM block. This PWM block shows you the parameters for the PWM. Got it? No? Okay. Now you can program your numbers. What? You already did this? Very good. But I was trying to figure out the variable. So you got a variable error. Now we'll get a fixed error. Don't worry. So in this PWM, there are two ways to supply the PWM. Motor not rotating? Motor not you are correct with some other manual. So in here, there is amplitude. So if you look at this plot, this is the amplitude. Can you see that this amplitude 400 is the same as this amplitude? Then you have this period. Now PWM can be specified either based on time or it can be specified based on number of samples. It is possible to go between these two, no problem. But in this particular case, PWM period up, down, forward. So PWM period is this guy. This is the period of the PWM. And this is given in terms of samples. The height of the PWM is given as 400. Then if you go down, the pulse width, which is basically this guy, this is 400. So which means the motor is on for the 400 samples and then it is off for 1200 samples. Then here there is phase delay. What do I mean by phase delay? Which means, I don't know if you noticed this, but when we ran this code, motor 1 rotates first, then motor 1 stops, motor 2 rotates, motor 2 stops, 3 rotates, 3 stops, 4 rotates. So what has happened is basically the phase delay is implemented for different PWMs. So this is third. And basically these PWMs are separated by phase. So you would see number of samples. So if you click on the second PWM block, I want you to click on the second PWM block and you would observe that the first PWM block has phase delay of 0, but the second PWM block has the phase delay of 400 samples. Everyone understood this? That is why you are actually sequencing through the motors. The last part is the sample time. Sample time TS. Now, TS is not in this particular case is 0.005. And where do you get this? If you go down, if you go to your simulation, you can actually type in TS and you would see 0.005. So what that means is every sample is being sent at 0.005 seconds. Everyone understood this? Now what I want to do is, I want to implement the exact same PWM on time. If I want to implement the exact same PWM on the time, that means this would be 400 multiplied by 0.005. The period would be 1600 multiplied by 0.005. So what I want you to do is, I want you, can't see the whiteboard. Zoom is blurring it. Yeah, sorry about that. I don't know how to deblur the, so let me see if there is, I don't know how to do it. Anyways, so at any rate, so what's going to happen is, if you go down here, you are going to feed different PWMs. Now, my question to you is, what I want to do is, I want to control the speed. So I'm going to do this simple experiment and let's see if this works. So rather than feeding a PWM, I'm going to go to simulation. I'm going to go take a constant and feed this over here. Oh, wow, Matlab smart, figured that out. And I'm going to change this constant value, the amplitude of the PWM, which is 400. So Tatvik, does it work?
I tried feeding the angle directly to the table. Like the water was flowing unreasonably.
Your stuff is connected to my Mambo.
But my parrot is not responding.
Your parrot is not flying. My parrot is ready to fly. So that's why I said, hold your. See, I'm not running. Did you see that? Okay. It doesn't work that way. Okay, everyone, don't power off your Mambos.
Yes.
You're getting data from my Mambo. Okay, finally, connection successful. Now what I'm going to do is, I'm going to go to hardware. I'm going to go to monitor and tune. And then see what happens.
So where is the gain actually applying? The initial gain which you said.
Initial gain?
The scroll. Where is that actually applying?
Which gain?
When you press start.
Oh, so basically the thing with the gain is, even though we are sending 400, it's not sending 400. When you say 10% of the gain, is basically it's just sending the 10% of the signal.
No, I didn't find the block. Where is it applying the power gain?
Oh, power gain, it is internal to the firmware. That is like a sort of a safety check. Don't know if it completed programming. Did it complete programming? No, it's not completed. It's still running the model on the Parrot Mambo server. Everyone's Mambos are turned off, right? So I'll run this again. So how many of you got your Mambos? Very good. Very, very good. Eric, where is your Mambo? Where is your Mambo? Now what should happen, guys? And that is what is happening. Hold on, Manohar. Hold on. Your laptop will connect to my Mambo. So please wait. Let me finish my experiment. Everyone understood that motor number 1 is just rotating and other ones are rotating in sequence? Okay. Students in the class, you understood this? You have your complementary filters working? Okay, so now what I want you to do is in next 10 minutes, it won't take more than 10 minutes. What I want you to do is open up your complementary filter code on your laptops. What? We'll start step by step. So everyone, please implement, bring your complementary filter codes. There is a different way of doing this, but I'll talk about it a little bit later. So you can actually generate your own PWM and control exactly the way this PWM is generated. But generating a PWM is not a trivial task. So you will need to run a triangular wave, then a comparator and all that type of stuff. So students who are in class, they're going to have all the fun. So open your complementary filter code. And now let's first understand the logic. Here is the task. Task number 1. I want the pitch stability. You agree with me? I want the pitch stability. So what would I do for pitch stability? The first, so one thing I didn't actually I didn't tell you that I must tell you. So what I want you to do is, when you ran this, did all the motors rotate in the same direction or 2 motors rotated in the opposite direction? No. When you did this exercise, did anyone observe? Yeah. So now observe. Okay, observe.
Pulses are, all pulses are positive.
Now what I'm going to do is, I'm going to send constant value to be minus and see what happens.
I think other wire is connected just to the ground.
So as you can see, if I change this to negative value, nothing happens. So which means if you want these two motors to rotate 1, 2, 3. Okay. Oh. It doesn't work that way. However, what I want to show you, and this is actually important thing. Can you see that I changed that from minus to plus and it started rotating? Now I'm going to do something else. I'm going to take this out from here. So basically I'm going to stop this. And I'm going to connect this guy here. I'm going to connect this guy over here. I'm going to connect this guy over here. And now I want you to observe very carefully. What? You're awesome, Patrick. You are awesome. So you know what experience is, right? Experience is the sum total of all the mistakes in the past. So yeah, I gave you both the drones. So what I want you to do is I'm going to start this again, and I want you to observe very carefully in what directions the motors are rotating. Yeah, I've made a mistake for logging. I'm going to start this again. So you would notice that the motor mixing algorithm actually takes care of the signs. So first two rotors, one left one. So left one is rotating clockwise. Motor, so I will write this down. Motor 1 is rotating clockwise. Motor 2 no, it depends upon the drone structure. No, the motor mixing algorithm, yeah, 1, 2 counterclockwise. Motor 3 clockwise, clockwise. And motor 4 should be counterclockwise. The structure so you have M1, M2, M3, M4. And what you want is you want to ensure stability about the pitch axis. So this is why. So what should happen? Your motor 1 and so let's see. When you have a negative pitch, when it's going down, you want motor 1. So if you have negative pitch, motor 1, motor 2 should speed up, and motor 4 and motor 3 should speed down. Are you with me? So now what I want you to do is, at least the students who are in class, go to your complementary filter code. So go to your complementary filter code. So I will have to close. Okay, before I close everything, online students, any questions? Because I cannot run two instances of Simulink coder. It will actually will not work. So any questions? Anyone wants to see the screen or what is being done? Now I'm going to close this and open the complementary filter. Everyone understood what's happening here? Question, concerns? Okay, so I'm going to close this and I am going to open hover, where actually I think I implemented complementary filter here. No, this is not, this is just I replicated PWM. So I think it's in here. Let me see if I implemented a complementary filter here. Oh no, I didn't implement complementary filter here. Where did my complementary filter go? Okay, let's so oh yeah, this is where I implemented this is where I implemented complementary filter. Okay, so what I'm going to do is I'm going to grab this motor mixing algorithm and put it over here. I'm going to grab this motor mixing algorithm and make it a little bit bigger. So please note, what I want to do is I want to increase the speed of motor 1 and motor 2 based on the theta, based on theta. So I'm going to grab this from here. So what I'm going to do is I'm going to have a gain block copy gain block, paste gain block, paste gain block. And what I'm going to do is there is actually something else that we need to implement, but let me give you what's happening here. So I would take this guy from here and then feed the output of this guy to 1 and 2. I would take this guy from here and feed the output to so 1, 2, it should actually decrease But to be honest with you, you don't really need it to decrease. You can just increase and that should be okay. So what I'm going to do is I'm going to use a constant for the time being. And I'm going to feed this constant value here. I'm going to feed this constant value here. And then what I'm going to do is, this is the gain. I need to add another constant. And I need to add addition operation. So sum. So this guy, this goes here. This sum is going to be here. So basically, and I'll tell you the reason for this sum. Because you want some baseline PWM to go. You don't want it to be 0. So this guy, then there would be a gain. The gain. This gain is going to fit over here. And then this baseline PWM would go over here. So I'm going to say the baseline PWM maybe is 200. This baseline PWM is 200. And this gain, I do not know if this is in radians or if this is in, no, my implementation is in degrees or in radians. So radians. So I need to choose appropriate value of gain. So now I'm hoping that my values would be valid for 15, 20 degrees. So my gain is going to be 15 divided by 180 multiplied by pi. This is the maximum value multiplied by what is this values? I'll start with 100. And then what I'm going to do is I am going to go to hardware, monitor and tune. Okay, it's start. Now let me preparing to take off. I don't need flight log, honestly. Okay, so basically if something like this happens, that means Matlab is not able to do the hardware. You can just do build, deploy and start. and let's see what happens. Can you see right now, all of them are rotating at baseline 200. Now observe what happens. Right now my gain is too low, so speed is not changing by significant amount. What I would do is I would increase the gain. Stop. So I would do 180 1 by 180 multiplied by pi, that gives me in degrees. So 1 degree. So let's see if I do it by 1000, what happens? Now all these motors should rotate at some baseline speed. Then when it goes up and down, it should basically increase or decrease the speed. It's not easy to see, right? So what if you want to check if your algorithm is working or not? Make this 0. Make this 0. Yeah, 200 is too small, I think.
You're feeding it zero, no?
Sit back. Clearly, there's some issue with my gain. Oh yeah, can you see? Oh, that's. Now the only problem is this will not work when it's going down. So what you want to do is, so check this out. So check this out, because as you know, negative PWM does not work. So what you want to do is, you want to actually power the other two motors. So as you can see, so now it is proportional to the. This is how you would do it. And I think now you have enough ideas and resources to get the Mambo pendulum working. I'm going to stop here. And if you have any questions, I would be happy to answer.